Hello. Well, today I'm going to start a review of the whole course. All right. So this is Math 239, Ordinary Differential Equations course. I think it's called Introduction to Differential Equations, but it's actually about ordinary differential equations. So I want to do quite a few short videos. Okay, and I'll do about 2 webwork sets for each video. So let's start right out and talk about sets 2, Introduction to ODEs, and set 3, Separation of Variables. First, I want to give this definition. A differential equation is a description of an unknown function in terms of its derivatives. Okay. And we can have ordinary differential equation or partial differential equation, depending on if it's a function of one variable or more. An initial value problem is a differential equation plus one or more initial conditions. The number of initial conditions is the same as the order of the differential equation. Like this one is first order, one derivative, will have one initial condition. All right. And then there's a big distinction in this class between linear and nonlinear ordinary differential equations. And then if they are linear, then there's a further subdivision between linear homogeneous and linear non-homogeneous. So let's think about this differential equation. I'm actually going to be doing almost the whole review of the whole course thinking about this differential equation. All right, the dependent variable here is y. Okay, it's first order, single derivative. It's linear, but non-homogeneous. There's no y squared, no sine of y's, no e to the y's. Okay, but there is that constant there. I can tell it's homogeneous. So I can tell it's non-homogeneous because y equals 0 is not a solution. Okay, so let's go on and talk about this. A differential equation is a description of an unknown function in terms of its derivatives. So there's this function. Now, we don't know if it's y of x or y of t. It could be y of x. So what this is really saying is y prime of x is minus 3 times y of x minus 20. Okay, this is really what that means. There's some function of x. Now this is a function of x on the left and a function of x on the right. And those two functions have got to be the same in order to have a solution. So let's just verify that y of x is equal to, let's say, 20 plus c e to the 3x is a solution to that ODE for any constant c. Okay. Now, what this idea of verification is very important. It's also a hard thing to check with web work, but it's an easy thing to check on a written exam. So let's do this. All right. Well, for this function, and it's nice to rewrite it up here before I differentiate, y of x is 20 plus a constant e to the minus 3x. And y prime of x is going to be 0 plus c e to the minus 3x times negative 3. We can simplify that as minus 3c e to the minus 3x. Okay? I didn't talk about set 1, the review of calculus. But in the review of calculus, you have to know how to differentiate in order to do differential equations. And in particular, you got to know the chain rule. You got to know the chain rule really well. Okay, forwards and backwards. In particular, hopefully you can maybe just go right from here to here and bring down the -3, okay? So this is the left-hand side of this differential equation when I plug in that function, okay? Let's think about the right-hand side. -3 times y minus 20. Okay, this is equal to -3 times what is y? 20 plus c e to the -3x, all minus 20. Oh, those guys cancel, and I get -3 times c e to the -3x. So the left-hand side equals the right-hand side. Therefore, I have a solution to the differential equation. In fact, in a way, we're done with this differential equation now. This is the solution to that differential equation if I assume the independent variable is x. And we have a uniqueness of solutions theorem that says that's the solution, that's the only one it can be. Okay, so in a way, we're done. We don't have to use any of these techniques I'm going to talk about. If we have that solution, we've got it, okay? The differential equations is a very goal-oriented subject. If you can find the differential equation and you didn't cheat by going to the internet and having somebody else solve it for you, that's fine. And how do you know if you got it right? A piece of cake. Differentiate, substitute it in, and see if it satisfies the differential equation. So in a way, that's all there is to the subject of differential equations. Okay, finding a function where if I substitute into the differential equation, I get the same function of x on the left as that function of x on the right. It's an equation that we call it an identity. This kind of equal sign means it's true for all x. Okay? All right. So, and in fact, this whole thing sort of flashes before my eyes. I see that, and I write down that, and I want you to be able to see that and write down that too, because you're so good at the chain rule that you say, yeah, if I differentiate that, and I subtract 20, right? So if I differentiate that, I get the same thing as subtracting 20 and multiplying by -3, okay? So end of story in a way. All right. But, okay. So that's the verify. This verify is very important. And if you can solve a differential equation by inspection and verify that it is indeed a solution, great. Okay. But suppose we didn't, suppose we can't solve it by inspection, and usually we can't. There's a few that we can. We have lots of techniques. We got this bag of tricks. The first bag of tricks is separation of variables. And I'll start with separation of variables by rewriting this as dy dx. So here's the same differential equation, which we're going to solve with lots of techniques. Now we're going to solve it with separation of variables. So we can formally think of dx as a unit that I can multiply both sides by dx and cancel the dx's. Remember, I can't cancel the d's, but dx I can think of as a unit. And for hundreds of years, from Newton and Leibniz on, people kind of thought of dx and dy as these little infinitesimals that I can mess around, move them around. Okay, so I can take this, multiply both sides by dx, divide both sides by y minus 20. It's kind of like cross multiplying. I can do dy over y minus 20 is -3 dx. This formal manipulation, okay? This ODE is separable, means I can separate it. This ODE is separated. This is separated. All the y's are on the left, all the x's are on the right, so I can just integrate both sides, and I get natural log of y minus 20 in absolute value is minus 3x plus a constant. Okay? So actually, along with the chain rule, which is the most important thing about differentiation, that's probably the most important integral, the one I did on the left. All right. So this is a solution. This is, in fact, an implicit solution. And an implicit solution means I've got just some expression involving the independent and the dependent variable, some equality that's true, that the equation satisfies, the solution satisfies. All right, but we often want to find an explicit solution. We want to find y as a function of x. Okay, so I can take e to both sides. I get absolute value of y minus 20 is e to the minus 3x plus c. Oh, and that is equal to e to the minus 3x times e to the c. Now this step right here is fraught with danger here, okay? People get this wrong all the time. At 239 level, at 400 level, at 600 level, people get, even professors, okay? So how do we do this? Remember, in order to mess with exponentials correctly, you might remember that thing I love to do is up on the right, I'll say x squared times x cubed is x to the 2 plus 3. And this, sorry, that's the one I just used. X squared cubed is x to the 2 times 3. And I can think about that as x times x times x times x times x is x times x times x times 5 times, right? Etc. X squared times x squared times x squared, there's 6 factors of x, okay? So why do I keep writing that? Because I use that here, right? Instead of x, I got e. Instead of 2 and 3, I got minus 3x and c. Right? What do I, okay? And how do I write this? Is e to the minus 3x times, that's the times right there, e to the c. Cool. Okay. Actually, a little digression. My wife was watching me do these videos. She says, sounds like you're teaching an algebra class, not calculus, not a differential equations class. And yes, most of your errors are going to be algebra errors, right? You got to know how to whip around those logs and exponentials and whip them around flawlessly. Okay. So, let's go on. We're trying to solve for y. Well, the absolute value of y equals something. That means y is plus or minus that thing. Okay, so let's go up here. I think I got room. Let's get rid of that. All right, so what is that? That means that y minus 20 itself is plus or minus, and we'll put the e to the c first, times e to the minus 3x. Actually, it's really nice that we had this plus or minus because this guy is always positive, right? So this is a positive constant. That's a constant that's positive or negative. Okay, the only thing this can't be is 0. But if I throw in 0, I still get a solution. Y minus 20 equals 0 means that y is 20, the constant function. That's good. So this becomes y minus 20 is, we'll call it another constant. We'll call it c prime e to the minus 3x. Okay? And c prime is plus or minus e to the c or 0. And so it's any constant. Not just a positive or negative constant. Okay. So that means that y is 20 plus c twiddle e to the minus 3x. Okay. And whether I call it c or c twiddle, it's an arbitrary constant. So this is the general solution. Is the explicit general solution. What do I mean by the general solution? Is for every c twiddle, I get a solution to that differential equation. Not only that, but every solution to that differential equation is contained by the proper choice of C. Twiddle. Okay, good. All right. So that's the first technique and a really useful one. And we'll be doing more videos about more techniques later. Bye.